Maple exploration of surface curvatures. In this webinar, I'm going to share with you my experiences in exploring, with the aid of Maple, the idea of surface curvature. Now, this is not a lesson in surface curvature per se. It's just a glimpse at how I used Maple to get insight into what I was reading in textbooks about this subject. So there are two paths to the curvature of a surface. One is through the Frenet curvature of certain curves in the surface. The other is through looking at the change in the surface normal as it moves in a direction tangent to the surface. Now that approach requires a directional derivative of the normal in a tangent direction. So I began with path 1, and that shed enough light so that I finally began to understand what they were doing in path 2. To follow path 1, we need to start with some definitions. So I use the expression Frenet curvature when I'm talking about the kind of curvature that you learn about in a multivariate calculus course. Okay, curvature vector, K. It's dTds, where T is the unit tangent vector, S is arc length. And P is the principal normal. And the length of that vector is the curvature, little k. Now we get into this notion of surface curvature. So normal section at a point P in the direction of some tangent vector. It's the curve that you get when you intersect a normal plane with the surface. So a normal plane contains the normal. You cut the surface with that cutting plane. The cut in the surface, the curve in the surface, is one of these normal sections. So it's a special curve lying in the surface. The curvature of that curve, and it's a Frenet curvature. You treat it as a curve in space. That's called the normal curvature. And the symbol here will be K sub n. The maximum and minimum of this normal curvature, and depending on the orientation of this tangent vector v, you're going to get different values for the curvature of one of these normal sections. Well, the max and min are called the principal curvatures, and they're designated K1 and K2. The mean curvature is the average of these principal curvatures, and the Gauss or total curvature is the product. So this is the plan that I followed as I walked along path 1. I took an example, took a surface. This was my surface. And I looked at one point, 115. I needed to get the tangent plane so I could get a family of tangent vectors, and I needed a normal. It was easily, well, the normal is easy to find. Okay, then I needed these slicing planes. I needed the intersection of the slicing planes with the surface to get these normal sections, these curves. Then I calculated the Frenet curvature of each of those curves, or that family of curves, and I obtained the extreme values, and typically there's a minus sign inserted, and we'll have to see where that minus sign comes from. So we look for the extreme values. You compare the extreme values of this curvature with the principal curvatures that you could calculate from a whole bunch of formulas you find everywhere. And then you can get the mean and Gauss curvature and compare that to what it should be. The calculations that I had to implement required a tool like Maple. There's no two ways about it. So now I'm getting ready to start working in Maple. I'm going to use the plots package. I'm going to draw some pictures. And primarily I'm working in the student multivariate calculus package, but there are some commands in the vector calculus package and some commands in the linear algebra package that I had to reach out to. These packages have commands in common, and you get all muddled up if you're not careful. So when I want something in either of these two packages, I alias this long name to something shorter. So VC, the vector calculus, LA, linear algebra, and then the surface, I use uppercase Z. So now we start computing some of the surface quantities that we need. Let's define the surface as a position vector R. So the parameters are x and y. X, y, z of x and y. Tangent vectors, Rx, Ry, derivatives with respect to x and y. Cross product gets us a normal, and then we have to normalize that, and that normal vector is uppercase U. So the vectors that we've just computed are position vector, two tangent vectors, normal, unit normal. And we want to work at the point P, so sometimes it pays to have those vectors evaluated at the point P. So I put a little p in the subscript xp, yp. Then I used n for the normal at that point, and uppercase N for the unit normal at that point. So those four vectors are tangent, tangent, normal, unit normal. Now at the point P, we want a family of tangent vectors. So we take a linear combination of the two tangent vectors, and I used cosine and sine, so I have a one parameter family of these tangent vectors in the tangent plane, and this is what that tangent vector looks like. And to make sure that I hadn't done something untoward, I drew this animation. The black vector is the tangent vector, the red vector is the normal vector, and it seems that as I go through 0 to 2 pi, I'm swinging that tangent vector through a circle. So that was what I wanted to do. Okay, now I need the tangent plane. So I use the plane command in the student multivariate calculus package. Point, tangent vector, normal vector. So this will get me the normal plane, and then I solved it for z, and I call that zp, z for the plane. This is the expression for those planes. And again, drew a picture to make sure that those planes did what I wanted them to do. So you can see the two red vectors are the basis vectors, the tangent vectors, Rx and Ry. This blue vector is the normal to the surface. The black vector is the linear combination of the two red vectors, so it's a tangent vector. And then I'm twirling the cutting plane, the normal planes. So you see that I've got this family of normal planes that cut through the surface. Then I wanted to see what it looked like if I put the surface in the picture. So I drew this picture. Now let's turn this a bit here so you can see that. So in red, you see the tangent, the plane, the curves. Right? These are the normal sections. These are the curves. The green is the normal direction. I drew it like an axis or an axle. You see the cutting planes. Okay, and the reason why this animation is slow is I use this intersect plot command here, intersect plot command, to get these red curves, and that's not a very fast command. So now I was ready to look at these normal sections, intersect, get these curves, get the curvature of those curves. All right. So here is the intersection step. This is the surface. This is the cutting plane, intersect, and it turned out there were two solutions. So I have got to look at these two curves, C1 and C2. I threw in t equals pi upon 4 to see if these curves pass through point P. And it looked like C1 passed through the point P, 115, but the other one didn't. So I said, okay, let me work with the curve C1. So I drew a picture to see what this all looked like. So these are the curves C1. There's the point P. And you'll notice way back here there's a different color. And I'm looking at these curves. And right here, there seems to be a jump. And if you look carefully, what you discover is that you switch from C1 to C2 for a very small range t. And that's traceable to that glitch that I found when I calculated the curvature of C1. So I used the vector calculus curvature command, and I timed this because it seemed to take forever, but actually it takes only 2 minutes to do this calculation of the curvature. So I drew the graph of the normal curvature computed by this recipe, and I see this funny thing down here, and I magnified a funny thing over here, and discovered that it's traceable to this jump from using C1 to using C2 for a very small part of the interval. But I went ahead and I computed the maximum and minimum of this curvature that I calculated, and I got these numbers. Then I did the calculation exactly, and I floated those numbers, and they match. So I figured, okay, I'm getting close. I'm on the right track. It's just that I got to worry about this glitch. For the moment, let's just see what else we can discover. So I got the principal normal, and here I use the vector calculus command for getting the principal normal. And by putting normalized here, it comes out to be a unit. And I looked for the angle between the principal normal and the surface normal. The principal normal on one of these surface curves and the normal to the surface. And it's essentially pi, except for this one place where you have this glitch. And this glitch is that glitch. But this pi explains the minus sign that is introduced when you look at the normal curvature, because these two vectors are opposed. So the literature is replete with various formulas for this stuff. Here's a formula for the normal curvature. All right, Kn is normal curvature. C is a curve. The second derivative, first derivative, norm squared. Dot that with the surface normal. Well, I see this and say, let me try it. Okay, so I need second derivative of, I use C1, dotted with the normal. First derivative, norm squared. And I'm evaluating at z equals 5 because that's the point P. And this curve is parametrized by z. If you go back here to where we obtained that, you can see why. It depends on z. This has x, y, z in it. This has x, y, z in it. I solve for x and y, so what's left? X and y are a function of z, so the curves C1 and C2 are parametrized by the parameter z. Okay, so this was kind of messy, and I did some simplifications, experimented around, and finally got it down to this expression. Nice closed form expression for the normal curvature. I drew its graph. Look at that. It's got the right shape, but there's no little glitch down here. So this thing does not have embedded in it that thing that caused the glitch. And I said, okay, let's get the maximum and minimum. So here's the maximum, and down here is the minimum. And you can use Maple commands for that, and you get these exact values. Therefore, I could get the mean curvature and the Gauss curvature from these two expressions. So at this point, I was feeling pretty good about where I had achieved, but I kept asking myself, all right, there are books that deal with curves that are not normal sections. So I said, okay, I got to investigate curves that are not normal sections. So I took some straight lines in the plane. X is 1 plus p cos t, y equals 1 plus p sine t. So cos t sine t takes this family of lines around in a circle. They all pass through 1, 1. P is the parameter along one of these curves. So I have now, then I lift those lines up to the surface, and I get some curves in the surface. This is what the position vector representation of those curves would look like. And here I've drawn a graph. The black dot is the point P. These curves lie in the surface, pass through the point P. They're not necessarily normal sections. Then I looked at this from above, and you can see that this is a family of lines. They all pass through the point P. Okay, so I said, let's get the curvature of that family of curves, and I call that little c. Parameter on any one of those surface curves is p. So I get the ordinary curvature, the Frenet curvature. I get this expression. Then I get the principal normal. There's the curve, c, unit, because I put normalized, use the principal normal command in vector calculus, and I get the principal normal. Then I construct the curvature vector, which is the product of the curvature and the principal normal. And so I now have the curvature vector. Now I want the component of the curvature vector along the surface normal. Since these are, this is a unit vector, if I take the dot product, simplify, assuming real, I have this expression with, oh, looks familiar. I had used this formula to get this closed form explicit representation of the normal curvature, and so I compare this expression to this expression, and lo and behold, they are the same. Now, as you read along this stuff in various textbooks, you come across this formula attributed to someone named, I guess it's pronounced Musnier. That's how I will pronounce it. And the formula is normal curvature is the Frenet curvature of any curve passing through the point P on the surface times the cosine of the angle phi, where phi is the angle between the principal normal on that curve and the surface normal. And this is used to prove or verify that the curve really doesn't matter. It's the tangent direction along that curve that determines the value of the normal curvature on that curve through that point. And where this comes from isn't, it's not black magic. Curvature vector is the Frenet curvature times the principal normal. The normal curvature is the component of this curvature vector along n. And since n is a unit vector, you take the dot product. So you replace k with kn, and you take the dot product. This, now they are both unit vectors. It's just the angle between. So I tested it out. I have a family of curves C. I get the angle between the principal normal, which we've already computed, and the normal to the surface. So angle command, and I test using this formula. I take K, which is the value of the Frenet curvature, times the cosine of this angle, and I get this expression. Looks familiar. I compare it to the earlier Kn that I computed. The difference is 0. So additional insight into computing of the normal curvature, any family of curves to the point. This business about the plane sections is not essential. Curves to that point, you have ways of getting the normal curvature without having to actually intersect cutting planes with the surface. Now, if you've done any study of surfaces, you would have run across the fundamental forms, first and second fundamental forms. So here's a quick review, because these things came up in my reading. All right, so the surface that we picked, position vector representation, second derivatives, rxx, rxy, ryy, at point P, this what these three vectors look like. First fundamental form, rx.rx, rx.ry, ry.ry. So it's a quadratic form. Second fundamental form, n.rxx, n.rxy, n.ryy. It's a quadratic form. For our example, these numbers turn out to be 17, 24, 37. So the matrix of the quadratic form looks like this. And the second fundamental form, for our example, turns out to look like this. It has these numbers. On the diagonal, -4, -6. And out front, 1 over the square root of 53. And it turns out that the normal curvature is the ratio of these two quadratic forms. And if this first fundamental form uses a unit vector, then the normal curvature is just the numerator, which is this quadratic form using the second fundamental form. Wow. So this result, that the normal curvature from which you get principal curvatures, from which you get the mean and Gauss curvatures, where did this all come from? But it's not black magic. If you look into it carefully, it's not black magic. So let's see if we can make this a little bit more transparent. Let's say the surface is given by position vector r, which is the function of x and y. The curve in the surface r of x of s, y of s, where s is the arc length. Unit tangent vector along that curve is drds. That would be a unit tangent vector. Now, how would you get that derivative? Well, you have to use chain rule. The r dx, dx, ds. The r dy, dy, ds. Curvature vector. Curvature vector is dt, ds. That's the curvature vector. So you have to take the derivative of this vector with respect to s. So this is what you're differentiating. This is a product. This is a product. So let's split that. You have the derivative of this product, you have the derivative of that product. Okay, and you're going to use the chain rule. You have derivative of this factor with respect to x, and you'll pull out another dx ds. And then you have to take the derivative of this with respect to y, and the derivative of y with respect to s. Then you hold this term constant and you differentiate this term and you get the x ds twice. One parallel case over here for this derivative are yx, xs are yy, ys. And then you multiply by this. Then you hold this constant and you take the s derivative of this guy and it's y ss. So now let's rearrange this stuff. You have rxx and an x sub s squared. You have r yy, what a y sub s squared. That's this term. Then you have two mixed terms, xy, yx. You have enough continuity here. You treat them as the same. You have an xs, ys. And then you have the two terms where r has only one derivative, but x and y have two derivatives. That's these two tail end terms. Now this is getting kind of messy because we have the parameter s so seldom. So sometimes you're going to be differentiating with respect to t, and then other times in the formulas you differentiate with respect to s. So let's do this. Let derivative with respect to t, the parameter that you have, be denoted by a prime, and derivative with respect to s be denoted by an overdot. So now this formula k, which is the Frenet curvature times the principal normal, that's r double dot. That's what this thing is, r double dot. And if you translate these expressions into this dot notation, you have rxx x dot squared, and then rxy x dot y dot r yy y dot squared rx, that's this one, and this is x double dot, and this is y double dot. Now, dot this with n. If you dot the curvature vector with n, you get the normal curvature. And we've seen that's Musnier's formula. It's the Frenet curvature times the cosine of the angle between. We've seen that before. But essentially what we want to look at now is the dot with n. So when n dots these three terms, you keep them. But when n dots these two terms, you get 0 because this is a tangent vector. Rx is a tangent vector. It's orthogonal to the normal vector. So these two terms go to 0 when you dot with n. Now look at what these terms are. N dot rxx. Well, if you remember what we did up here, n dot rxx, n dot rxy, n dot yyy. Those are the numbers that show up in the second fundamental form. That's probably why people looked at it. Okay, so we use the letters little e, little f, little g for those dot products. Now I'm looking at x dot square. Now this is derivative with respect to arc length, but you never have arc length, so you use the chain rule. The x dt, dt ds. And then you're going to have the x dt, dt ds from this fellow, and dy dt, dt ds from this fellow. So again, you get dt ds squared. And here's y dot squared, so it's dy dt, dt ds, and you square that. Okay, pull out the dt ds squared, and put it in the denominator as ds dt. Okay, so the numerator is in the form of this second fundamental form, quadratic bilinear form. Okay, the numbers E, F, F, G, X prime, Y prime. That is a vector you could easily compute. If you put it here as its transpose and you put it here as a column vector, right, then you are getting this numerator, and there's that quadratic form we saw in this what at first glance appeared to be magic formula for Kn. Okay, remember this is all giving us Kn. Now let's look at this ds dt squared. It's the length of the tangent vector squared. How would you compute that? Well, here's one representation. R sub x, right? How do you get this? It's the r dx x dt, the r dy dy dt. So you have to take the dot product of this expression with itself. And at first glance, you would think you multiply these two and you multiply these two. But when you write these vectors out, you realize that you have two binomials multiplying each other, so you get cross terms. And here are the cross terms. And so you have rx dot rx, rx dot ry, and ry dot ry. And if you go back and say first fundamental form, you realize that these are the numbers that appear in the first fundamental form. And so you can put those numbers into the first fundamental form, and you put the tangent vector components x prime, y prime, which you can easily compute, into here to transpose and here to column. And you have the first fundamental form in the denominator, which is exactly what this thing said right here. So there's the connection between first and second fundamental form and the normal curvature. So having worked that out, figure let's apply that to one of our examples here. It should be a piece of cake. We should be able to verify all of this. Okay, so we need the curve, family of curves. So we have that. These are the ones where we put straight lines in the plane and lifted them up to the surface. And then we compute a tangent vector using the derivative with respect to the parameter that we have. That's the equivalent of the t, right? That's the parameter that we have. It's not arc length. Okay. And now I'm going to form these bilinear forms, the first and second fundamental form. And I say, wait a minute. The matrices for these two forms, they're 2 by 2s. Okay, look, they're 2 by 2s. I've got a tangent vector that's 3-component vector. And it took a long time for it to dawn on me that you have to express this tangent vector in terms of a basis for the tangent plane. Okay, so Rx, Ry are a basis for the tangent plane. And I'm working at the point P, so I use the numeric Rxp, Ryp. I take a linear combination of these two vectors, and I equate that to this vector v, and I want to know what are the a and b that allow me to represent this vector in terms of these two vectors. And so that pair AB is now a 2-component vector in the tangent plane V. It turns out to be cos t sine t. Maybe that was obvious, but it wasn't obvious to me when I was working my way through this stuff. It says, okay, I'm going to get the bilinear form, second fundamental form, bilinear form, first fundamental form. Linear algebra has this bilinear form command. Is very convenient. I make this ratio, do a simplify, and I get this expression lambda. It looks very familiar. I compare it to the kn that I computed earlier. The difference between them is 0. This does work, but the secret here was to realize that you have to express this tangent vector not as a vector in space, but as a vector in the tangent plane. As you start reading these more modern books, you run across this thing called a shape operator. And the curvature, surface curvature, is discussed in terms of the shape operator. All right, what is the shape operator? U is a unit normal on the surface S. Chi, depending on that unit normal and a tangent in the tangent plane, is the negative of the directional derivative of U in the direction of the tangent vector t. So that takes a vector in the tangent plane to another vector in the tangent plane, because that's what the directional derivative of U will give you, another vector in the tangent plane. This mapping is called, I guess it's Weingarten, because it's probably a German word. So Weingarten or Weingarten, take your pick, has as a matrix representation this matrix W. And W can be given in terms of the product of these fundamental forms. So first form is you do it inverse, second form you don't. It gives you this matrix, and this is what it looks like for the example we've been working on. Now I've just got to do this aside because it poses the question that plagued me for a long time, as I just said before. You compute a normal vector. It's got 3 components. It's a space vector and a tangent vector. It's a space vector. It's got 3 components. Shape operator has 2 components. It's a 2 by 2. How can you get anything with this mix match? I went to the internet. This was the site I got to. It's a physics forum. This very question was asked. The dimensions don't seem to match, right? See, 2 by 2, right? In all of the replies, and I went through all of these replies, nobody ever points out in any of these replies that you've got to express the vectors as 2 component vectors in the tangent plane. And until I figured that out, I was at sea. Let's see how that factors into what we do next. Okay, with this insight, let's see if we can construct the W matrix from first principles. Let's take directional derivatives of the normal vector in these tangent directions and see what happens. Okay, I want to use the directional diff command in the vector calculus package. All right, this command says display vectors as column vectors. But everything has to be a vector field. So I have to redefine everything that I need as a vector field. So Rx, Ry, U, and a tangent vector. Define them as vector fields. And we'll work this tangent vector at the point 1, 1, 5. Okay, so here are the vectors as vector fields. Okay, so I want to take the directional derivative of this unit normal in these 2 tangent directions. So directional diff of this vector, it's a vector field, in this direction, and I evaluate at 1, 1. Do the same for this direction. So I call the resulting vectors M1, M2. See, you put the minus sign because so the definition says you put the minus sign. Okay, so I get these vectors, but they're three-component vectors. And here's where that wonderful insight comes in. You got to express these in terms of the tangent basis vectors. Here are my two tangent basis vectors. So I do that same trick. Equate, solve for the AB. These now have two components, and I call them capital M1, M2. And you look and you just say, it's just like you knocked off this third component. But until I had a reason for doing that, it made no sense. Okay, then the basis vectors in the tangent plane are essentially your I and j. So when you ask what is the matrix that's going to take the the tangent vector to the directional derivative, it's going to be just the columns of that matrix are just going to be these two vectors. So this is the matrix you end up with, and that is in fact W. And here is a check that these directional derivatives are actually vectors in the tangent plane. You dot them with the normal, you dot them with the normal, you get 0. They are in the tangent plane. Okay, what are the consequences of getting at this shape operator? Okay, it's a 2 by 2 matrix. Its eigenvalues are the principal curvatures. Just think about that for a second. If you think of the Rayleigh quotient, which is a bilinear form, by extremization, max and min, of that bilinear form, you can extract eigenvalues. Okay, so it makes sense that the principal curvatures would be the eigenvalues of W. I can accept that. Therefore, half the trace is going to be the mean curvature, and the determinant is going to be the Gauss curvature. If you get the eigenvalues of W, these will be what they are, and they look familiar, and you float them, these are the right numbers. If you look back for the mean curvature and the Gauss curvature that we had obtained earlier, and you compare that to trace and determinant, they're the same. So if you understand that shape operator business and can get those directional derivatives, you can extract the principal curvatures, mean and Gauss curvatures more efficiently than we did the older way, which was to get curves and get that curvature, etc. Well, we've pretty much nailed this business about surface curvature, but as you read the literature, you will run across two other things. One is called the Gauss Map. Gauss Map says, treat the components of the unit surface normal as if they were components of a parametric representation of the surface. Well, that's easy enough to do in Maple. There's the surface. I saw these little curves in here, and I said, okay, let me animate the space curves, right? Space curve. That this doing this to the principal, to the normal vector would do. And you get these curves on the surface. That's what these curves on the surface are going to be. Right? I said, what if you take a curve in the plane, and I just took some circles, and see what that does. Okay, so that's what happens. This is what it looks like. Conclusion that I drew, I don't know what the Gauss map tells me. I don't see any additional insight from the Gauss map. There was one more concept that I ran across. At first thought it had something to do with surface curvature, but then I realized this thing called geodesic curvature of a surface curve. It's curvature of a curve in the surface. It's not curvature related to the surface per se. It's curve in the surface. And there are two different definitions given. This will be the symbol, kg, geodesic curvature, of a curve. It's the Frenet curvature of C hat. And C hat is the orthogonal projection of a surface curve onto the tangent plane. Here's another way of looking at it. Frenet curvature vector K gets projected onto this unit vector, zeta, n cross t, normal, tangent. So this is necessarily in the tangent plane, and there is a formula or expression for it, c double prime, n cross c prime, length of c prime cubed. Let's implement this first approach or first definition. We need a curve. So I go to the family C. This is the one that has the lines in the plane lifted straight up. And I pick one curve. So I pick a curve by giving a value of t. And that's going to be this vector. Then I need a representation of the tangent plane. So I use the tangent plane command in vector calculus. This is the tangent plane. I think we've seen that already. So to get the projection of this vector onto this tangent plane, I look at their difference, take the norm, so I get the distance between squared. Get rid of the square roots. So here is the distance between, and I want to minimize that distance, so I use calculus. Take the derivative with respect to x, take the derivative with respect to y, set it equal to 0, solve for x and y. This x, this y, I plug that back into the representation of the curve, and I have this projected curve. And of course, I want to draw a picture to see if what I did was okay. So I believe this is the tangent plane. This is the curve in the surface that I want to project onto the tangent plane. And the red guy is the projection into the tangent plane. And if you look at it just right, they line up. So yes, this appears to be the projection. The red guy, which is this, that's CP, appears to be the projection into the tangent plane. And all I do is compute the Frenet curvature of that red curve, that's CP. I get this number. But until I can verify that somehow, it's just the number. In the second approach, we are looking to use this formula. What are the ingredients? I'm going to use this part here. Curvature vector. Now we had it for the family. We want it for just one member of that family, and that one member is the curve where t equals 0. Tangent vector. Well, this will give us the tangent for every member of the family. This picks out one member of the family, and this puts us at the point P. So that would be this vector. And then I need n cross t. Right? That's n cross t. That's the zeta vector. And a dot product with k. That should give me kg. And this number, let's see if we can see them both on the screen at the same time. This is what we can obtain using the first approach. This is what we obtain using the second approach. And then I wanted to visualize these different vectors. Okay, so what do we got here? We have the black curve is the curve in the surface. Tangent plane, projection onto the tangent plane. Right? That's the red curve. It lives in the tangent plane. Green vector, that's normal to the surface. Black vector is tangent to the curve in the surface. And we have this gold vector, we have this red vector. This is the Frenet curvature vector for the red curve which lies in that tangent plane. The goal vector is zeta, okay, and it is the projection of the red vector onto this goal vector that gives you the geodesic curvature, and they turn out to be the same.